We will now be looking at atmospheric pressure. Before we can fully appreciate atmospheric pressure, it is important to study the following concepts. The force and pressure associated with now a certain known mass of matter. Force. This is calculated by multiplying the mass of an object by its acceleration. And we use this equation here. So, if you want to calculate the force exerted by a known mass of matter, you multiply its mass in kilograms by its acceleration. But in this case, we are only interested in knowing what is the force exerted on that piece of matter by the acceleration due to the Earth's gravity. So anything that has mass exerts a downward force due to the Earth's gravity in it. An object of 1 kilogram, for example, would exert a force as calculated by the following equation. So it will be force will be equal to 1 kilogram times 9.8 meters per second square, and that is equal to 9.8 newtons. 9.8 meters per second square is the acceleration due to gravity. So if you want to know what is the force of an object on the Earth, you multiply it in kilograms times the acceleration due to gravity on Earth, which is this. If you go on the moon, the acceleration due to the moon's gravity will be 1/6 of this. That is why when you go there, you weigh 1/6 of what you weigh on the Earth. So that is about force, how it is calculated by multiplying the mass of the object in kilograms times the acceleration due to the Earth's gravity. Pressure. If you put a block on the floor in your home or on the ground, that block is having a certain mass, and associated with that mass is a certain force. So if you have that block resting on your finger or something, you will feel a certain pressure. So this is how pressure is defined. It's defined by the force that is acting on a certain area. If a force of 1 Newton, for example, is applied to an area of 1 meter squared, then the pressure exerted on that 1 meter square will be equal to this. You take the 1 Newton and divide it by 1 meter square, and the pressure is expressed in Pascal, okay? 1.0 Pascal. So here is a block, for example, that has a force of 1 Newton on an area of 1 meter square. Then this is the pressure that will be felt by the surface beneath it. Now look at this equation here. What will happen if we keep decreasing the surface area? What will happen if we keep decreasing this value here? From a mathematical point of view, the pressure will increase. So if I had the same 1 Newton here, but look what happened. I'm reducing the surface areas on the floor or on the ground. Definitely the ground will feel a higher pressure by virtue of what we are seeing here. And more so, look what happens. If we take that and we put it on top of a needle, now what is going to happen there? It will exert a very high pressure on whatever this needle is sitting on. And that is why when you sharpen your knife, you're making the surface area very small, and therefore whatever force you're applying will cause your meat or whatever to cut quicker than if you didn't sharpen it. Same thing has to do with a hypodermic needle, right? They have very fine point, so when you apply a force, it creates a high pressure that allows it to pierce the skin very easily. Now we'll talk a little bit about the Earth and its atmosphere now. This diagram is trying to depict the Earth that is surrounded by this blanket of air that is called the atmosphere. Does air have mass? What little experiment can you carry out to prove that air has mass? Anybody? Okay, the one that my students will tell me is, sir, you take an empty balloon, you weigh it, then you blow air into it, tie it up, and you weigh it again, And you'll find when you weigh it afterwards, it will weigh more than the empty balloon. So that's a little experiment to show that air does have mass. So because air has mass, it will also have a force. Because of the Earth's gravity, it will have a force acting down on the Earth. And it will create also the pressure. So this is what we mean by atmospheric pressure. And this is what it looks like. Watch this. At sea level, the force exerted by the atmosphere is 101.0 kilonewton. The pressure exerted on an area 1 meter square by the atmosphere on the Earth would be equal to this force here, which is this, okay, divided by this area here. That's the force divided by the area, and this is what it is, that kilopascal at 0 degrees Celsius. How does this translate into some type of mass that the layman can appreciate? What mass will create this force? This is what it is. Look, 11.08 tons. So if you have a mass of 11.80 tons and you allow that mass to be pressing on the Earth of an area 1 meter square, this is equivalent to the atmospheric pressure. Can you imagine that? So let me show you this figure here. Look, if I make a box that is 1 meter by 1 meter and I put inside something, a fluid, sand or something that is weighing 11.08 tons, that is the mass of air that's pressing down on the Earth's surface, that it has an area of 1 meter by 1 meter. So that's an awesome mass. So point is this now. At every point on the Earth's surface, we are having the atmosphere pressing down on us with that very high pressure. Is equivalent like having these boxes here, and you put 11.08 tons of mass in it, and it's pressing on the Earth's surface with that force, that mass there, creating a big force there, and that's creating that pressure in the Earth. Why don't we buckle under that pressure? Why we don't feel this thing squeezing down on us? We don't feel it squeezing down on us because we have become adapted to living on Earth, where our blood pressure and the combined osmotic pressure from the tissues of our body are equal and opposite to that of the atmosphere's pressure. Our body is amazing. Next point I want to make is this. Look, if you are at sea level, that is the pressure that will be felt. Anyway here, atmospheric pressure is acting in every direction, right? Because this is the Earth here. If you whether you're standing on it or sideways, the gravity is pulling everything towards the Earth's center, okay? Now, if you're living in a mountainous area, if you go up high into the atmosphere here now, right? This is point A, and this is point B here. That's at sea level. So something is placed here, and something is placed here, 1 meter square, 1 meter square here. Which point will experience a greater pressure, A or B? If you said B, you're correct. If you say A will experience less pressure because, look why. Only this column of air will be acting on it, and therefore the force due to that column of air will be less, and so the pressure is going to be less. That's why I made a point that people living in mountainous area now, right, will feel less pressure than people living down there. So that's why when you live in mountainous areas, you have to adapt to living at a lower pressure. And we spoke about the problem that people having to cook up there. So that is a little bit about the atmospheric pressure and how phenomenally high it is. All right. Now, how do we demonstrate atmospheric pressure? How can we show someone, hey, indeed this atmosphere is pressing down? One way of doing that is by having it crush an empty pop can. How do we do this? This is done by placing about 15 milliliters of water in an empty pop can, and you heat it on a hot plate until all the water is boiled off. When that happens, using a pair of tongs, you take the can quickly and you invert it into a beaker of ice cold water. And you can see in front of your eyes, all of a sudden you see in a dramatic way, the can crushes by itself. It implodes just like that. Let us explain why that happens. So first of all, this here is your empty pump can, and we put in a little bit of water down here, about 15 millimeters. In this empty pump can here, the atmosphere is pressing on the outside of the can, but the air particles inside here, so whatever little bit of water vapor present here, these particles here are also exerting a pressure on the inner walls of the can. So the atmospheric pressure is pressing on the outside of the can, and the air particles inside there, along with any little bit of water molecules that evaporated there, are pressing on the inside, and these two balance off each other. So the pressure on the inside of the can is the same as the outside of the can. Okay, now this is what happens. Look here. As the water boils, it creates a current of steam that takes away the air particles with it. That is why a minimum amount of water needs to be placed inside here, such that when it is boiled, it creates enough steam to take away all the air particles out of the can, such that only water vapor will remain here. We can now compare the new pressure within the can with that of the atmosphere. The water molecules now, instead of air, will be exerting a pressure on the inside of the can, and here we have the same, that nothing is happening with the atmosphere, is always acting on the outside surface of the can. So in this figure B here, we are only having water vapor present. Why do you think we wanted only water vapor to be present there after a time? Because we know that when the can is subsequently cooled, the water vapor within will condense and a partial vacuum will be created in the can. If air particles such as oxygen and nitrogen are present, they will not condense, since they will need very low temperatures to do so. So when the can is inverted into cold water, condensation takes place. Now there is no air particles nor any water molecules there that are creating any pressure on the inner walls of the can. But because the atmosphere is always there, it crushes the can. So this is a cute way of demonstrating atmospheric pressure. You put about 50 milliliters of water inside there. Initially, the inside pressure is the same as the outside pressure. Air particles are exerting a pressure on the inside walls. Atmospheric pressure is exerting a pressure on the outside walls. When you boil this, it creates a current of steam. As it keeps moving out like that, it takes all the air particles out of the can. Eventually, you'll only have water molecules inside it. We call that water vapor. When you invert this can now into the cold water, it causes the water vapor to condense, and when that happens, a vacuum is created, so there's nothing to push out against the atmospheric pressure, and that's why the can crushes. Now we're going to talk about Italian scientist Evangelista Torricelli. What he discovered was this. He discovered that if you fill a tube with mercury and then you stopper this tube and you inverted that into a container of mercury, after which the stopper is removed, and if the tube is of a certain minimum length, some of the mercury will fall out of the tube, but some will still remain. And when you measure that amount of mercury from the bottom here, from the bottom to the top there, it is found to be 76 centimeters. So he concluded that atmospheric pressure is capable of supporting a column of mercury 76 centimeters high inside a tube. Another way I try to explain this was like this. If I have a vacuum tube here, made of glass, and I insert that into a container of mercury, and I then break the bottom here. Spontaneously, the mercury will rise up the tube to a certain height. This is another way of demonstrating that atmosphere is having a pressure. I create a vacuum here, I break the end of that tube there, and then wow, you see the mercury is going up there. And it stays at a height of 76 centimeters. That is happening, or that happened, because the atmospheric pressure is pressing down on everything. It's pressing down on that liquid there, it's pressing down on my head and your head. Everything is pressing down on. But we're not feeling it. But this vacuum experiences that. As it is broken there, the mercury rises inside it and stays to that level. Why you think it will stay at that level only? Because watch, this mercury by itself has mass. It has mass, it has density, and that by itself is exerting a downward pressure on the surface of this mercury here, okay, down here, and that is why it will not keep going up more and more, because the atmospheric pressure will not be able to sustain that height there. It can only be able to support that column of mercury. So as it reaches that level there, it starts to create a pressure that is equal and opposite to that of the atmosphere. So that is the discovery of Torricelli. And I'm giving you some question here. Oh, I answered this already. Why didn't go up more than that? What measurement will be obtained if this activity is done on top of a mountain? How you think that height of the mercury is going to be? Or you use water instead of mercury. And I give you some hints here. On top of the mountain, atmospheric pressure is less than sea level. The pressure due to a column of liquid, P, is due to the height of the liquid times its density times the acceleration due to gravity. Next, mercury is 13.53 times density of water, which is 1 gram per milliliter. So with these clues here, I hope you'll be able to answer these questions here. What would the readings be if Torricelli had done that on top of a mountain, or if he had used water? I want to talk to you a little bit about this guy here, submersible. Remember last year, 5 or 6 people went down in this Titan here. They wanted to go to see the wrecked Titanic, and there was an accident, after which not a shred of the remains was found. See what happens? That Titanic there is about 2.4 miles down from the surface of the ocean. And the pressure down there is 500 atmospheres. My God. 500 atmospheres. Remember 1 atmosphere, I said, was 11.08 tons of weight. If you multiply this by that, and you can imagine what pressure that was exerted in that submersible. These people didn't have time to think, because they were decimated. They just become fragments of cells. They just disappeared in less than a fraction of a second. I'm just talking about this because I want you to know also that as you go deeper and deeper down into bodies of water, such as in deep sea diving, certain risks are involved that people should be aware of, and to take the necessary precautionary steps to avoid injuries during these type of activities. So units of atmospheric pressure. You have the milliliters of mercury we talk about, okay, discovered by Torricelli. Then you have torrs, in honor of Torricelli. 760 torrs is equal to 1 atmosphere, okay, same as 1 atmosphere. So 1 milliliter is 1 torr, all right. Then you have Pascal, a name after Blaise Pascal, French scientist, okay. So the SI unit of pressure is symbolized as PA, and it is a pressure exerted by a force of 1 Newton over 1 square meter of surface, okay. Since it is very, very small, they speak about kilo and megapascal. Bars, this unit is used by meteorologists to express pressure. 1 bar is equal to 100 kilopascals. Next, atmosphere. Of course, we've spoken about that already, and it is in kilopascals. And this is used to express high pressures. For example, when you do the Haber-Bosch process by which ammonia is synthesized, they use up to 152 to 200 atmospheres of pressure to pressurize your hydrogen and nitrogen gas together such that you can get them to react. Remember, nitrogen is relatively very stable, triple bonded. That's why you have to use a very high temperature and pressure to combine that with hydrogen to make ammonia. Okay. Finally, we have to report under what conditions of temperature and pressure certain experiments are done. For example, if you want to tell somebody about the volume of a gas that you collected, say in Canada, you will have to tell the person at what temperature and pressure you collected this gas, because both temperature and pressure affect the volume of a gas. Okay? Originally, the conditions to which some experiments were confined to, and for reporting some things produced such as gases, were 0 degrees Celsius and 76 millimeters of mercury as a standard, okay? And that is known as standard temperature and pressure. So if you wanted to measure some gas, what you'll have to do, you'll have to create conditions for doing the experiment where the temperature is 0 degrees Celsius and the pressure is 76 centimeters of mercury. So that was changed by the International Union of Pure and Applied Chemistry in 1970, because experiments are done in ambient temperature, with surrounding temperature, right, which is about 25 degrees Celsius, and where the pressure is always nearly 100 kilopascals. So this is what is meant by standard ambient temperature and pressure. These ones here, okay? Standard temperature and pressure refer to these two conditions here, and standard ambient temperature and pressure refer to these two conditions here.